Bismillahirrahmanirrahim. Welcome students to the online lecture of Digital Logic Design. In today's lecture, we will be discussing the binary arithmetic. In the previous lecture, we discussed the number systems and the conversion among the number system. In the current lecture, we will be utilizing these concepts for the binary arithmetics. This part of the course belongs to the course learning outcome 1. First, we will be discussing the binary addition. We are discussing this thing because the main aim is that we should design, or we should be able to design a system which could perform these things for any digital system which can work on the digital or binary systems and perform the addition, subtraction, and the other operations. This is you can say a smaller part of the arithmetic logic unit which is present in all the processor systems. Suppose we have two numbers here. One is x and other is y. Both of them represent a single bit or single digit numbers. Both of them could have either value of 0 or 1. So we could form 4 different combinations depending upon the values of x and y. Either the x and y could have, both of them could have value of 0, either both of them could have a value of 1, or either of them could be 1. So we will form 4 different combinations: 0 0, 0 1, 1 0, and 1 1. The result here will be represented in 2 bits. One is the main result, which is represented in the sum bit, while we'll also have a carry bit. For the first case, let's see that. For the first case, we have two numbers, one bit numbers, x and y. Both of them have value equal to 0. So if we add both 0 plus 0, we will get a sum of 0. So in the next case, if we have either x equal to 1 or y equal to 1, and both of these cases, this will result in a sum of 1. Well, for the last case, when both the x and y have a value of 1 1, in this case we will have sum equal to 0 while carry equal to 1. This is because if you see that 1 plus 1 is equal to 2, and for representing 2 in binary number system or decimal 2 in binary number system, we need at least 2 bits. This can't be represented in a single bit. So for this one, we can combinedly represent the result in form of this carry and sum bit. So if you see that this 1 and 0, if you combine them in binary 1 0, it will give a decimal equivalent of 2. So for in this case, our complete result is represented by both sum and the carry bit. So in this case, we will get a carry equal to 1 while we'll have the sum equal to 0, and this combinedly represents the value of 2, which is the actual result of 1 plus 1. In this example, we have discussed only a single digit or single bit numbers. Now suppose if we have any other numbers which are represented in, say, m number of bits, then in that case we have to design our system in such a way that it can perform addition between different n bits. If we have two different n bit numbers, in this case, the result will be represented in n plus 1 bits. For example, in this case, both of them were represented in 1 bit, means n was equal to 1, but the complete result is represented in n plus 1 bit, means 2 bits. So if we have, say, two 5-bit numbers, then the result could be accurately represented in 6 bits. Suppose we have x and y here. Both x and y here are represented in form of 6 bits binary number. This is x and this is y, and we aim to perform the x plus y. What we do is we first simply write them in this form, and we will follow the same structure we generally use to add two numbers into decimal number systems. We will add the numbers column wise. First we will add these two numbers 1 1 column wise. If we have a sum here, we will write the sum here, and if some carry is generated, that carry would be written here. Similarly, the result of the next column would be represented in a sum bit here, and if there is a carry generated, that carry would be written here. Similarly, we will move on to the next column. So for this first case, you see that for this two numbers 1 1, we will just look at this table. In this table, you can see that the result is equal to sum is equal to 0. So we will get a 0 here, but we will also get a carry to the next column. So we will have a carry here. So again, when we will have a carry here 1, then 1 plus 1 will again result in 0 here, and that one will be transferred here. In this case, now we will have, you can say, 3 ones here. We will first add the 2 ones here, which will generate a carry of 1 to the next column, and while we will adding the 0 and the 1 here, then we will get 1 here. So in this way, we will calculate the addition process by performing the addition column wise. If a carry is generated, we will move that carry to the next column, and then we will keep on adding the numbers in. The last number represents the final carry that is generated here, because if we finally add these two number here 1 1, it will get the result equal to sum is equal to 0 here, and we will get a new carry. So that carry will be straight away represented in this form. You can easily check that whether our this operation is correct or not, because you can always convert these binary numbers into the decimal equivalent, and then you can perform the decimal addition and check that whether that result of that decimal addition is the same as this one or not. So this is how we perform a basic addition between any two binary numbers. Next one is the subtraction. For the subtraction, we follow this table. We have two numbers x and y. Both of them are represented in a form of a single bit or single digit numbers. We will have 4 different combinations of the two inputs x and y. The result is represented in a form of a difference, and if we are subtracting it from a greater number or a smaller number, we will also need a borrow. So this bit represents a borrow here. So for the first case, if you just look at that, for the first case, we have 0 minus 0. In this case, we will get the difference equal to 0. For the next one, we are subtracting 0 minus 1. And this one, this y is bigger than this, so we need to borrow a 1. So what we do is, in this case, we will get a difference here equal to 1, and we will also get a borrow that is also equivalent to 1. Why? Because the difference is 1, because when we are subtracting 0 minus 1 and we have to borrow 1 from the next column, we will get 1 here. So that 1 will make basically this value decimal equivalent to 2. So 2 minus 1 will result in difference of 1, and because we are also taking a borrow, that's why we are representing 1 here. The next one is that 1 minus 0 will result in a difference of 1, while in this case we will have borrow equal to 0. And the last one, we just subtract 1 minus 1, it will result in the difference equal to 0. I mean, also have a borrow 0. Again, we have subtracted these two numbers by considering that both of numbers were represented in a single bit. Now if we consider that both x and y are representing any 6-bit binary numbers, so we will see that how we can subtract both these numbers. This is x and this is y. Again, we will be trying to relate it to the decimal subtraction part, because most of the process is almost the same. We will do it column wise. First we will look at this column, subtracting 1 from 1. We will look at this table, will result in the difference equal to 0. So we will get a 0 here. For the second one, we have 0 minus 1 here. In this case, 0 minus 1 case, we have to borrow a 1 from the next column. So what we do is that this 1 will become 0, and we will get a 1 here, 1 here. So this 1 0 will make it 2. So 2 minus 1 will also give us 1 here. So similarly, we will keep on carrying the same thing from the next and next and the next column. If we require borrow, we have to look for the next and similar next columns. You have to consider one thing, that the smaller of the two numbers should always be in this position. to accurately get the subtraction part correctly done. So the final result here is that just we perform the column wise operation according to this table, we will get this result here. So this is the subtraction between the two 6-bit binary numbers. Now we will move to the multiplication part. Multiplication is quite similar to the one which we do in the decimal part too. We have two 3-bit numbers x and y. We need to multiply them. First we will do is we will take only this first digit and we will multiply it with this one. So this 1 into 1, then 1 into 0, 1 to 1, we will get the same number here. So the first row is same. For the next row is what we put is we put x here. You can just leave that space. Please don't confuse this x with this one. This is the variable and this is just for the normal multiplication thing. We will get 0 here because in multiplying 0 with all this number will result in 0. Similarly, the last row we get is that we get 1 multiplied by this one, we will get 101 here. Now once we have done this, now we need to add all these numbers, because you know that multiplication is also kind of a repetitive addition. So in this case what we do is we just add all these numbers column wise. So if you just look at the first one, here we only have 1, so we will get 1 here. For the next one we will get 0 here. For the third one we have 2 ones here. So in this case we will get a sum equal to 0 here and we will get a 1 carry here. So we will get 1 and similarly 1 here. So this will be the final result. You can again always verify whether your result is correct or not. Just simply convert these numbers into the decimal equivalent and check that whether their multiplication results the same number whose binary equivalent is equal to this one. Now we will be discussing an other thing which we call the complement thing. Because if you see the last three things that we have discussed in this lecture, the addition part, the subtraction part and the multiplication part, you have seen that probably the subtraction part is the most complex or the difficult one, because we have to consider a lot of things when we are subtracting any given numbers. The first one is that what is the exact place for a smaller number and a higher number, we have to decide it. So we need a comparator before doing the subtraction part, that whether which one is the greater and which one is the smaller. And the next thing is that the borrow thing. We always have to look to the next column to get a borrow. So if there's a now borrow from the next column, we have to look from the next column after that. So we have to consider a lot of things in the subtraction part. There is a thing which is known as the complement, which we are discussing now, which will be very helpful in simplifying this whole subtraction process. In fact, it is a way in which we can use a single hardware for both the subtraction and the addition part. By using the complements method, we will be able to design a single hardware system that will be able to subtract and add any two given binary numbers. So we will first be discussing only the complements thing, how we will be calculating the complements, and in the next lecture we will be utilizing these complements in the subtraction. Complements are used for simplifying the subtraction operation and for the logical manipulation. Suppose we have a number and we take its complement. If we take its complement twice, that will result in the original number again. Generally, there are two types of complements that are considered. The first one is known as the radix complement or the R's complement, and the next one is the diminished radix complement, which is also known as the R minus 1 complements. So for any given number system, generally we calculate two different types of the complement. One is the radix complement, R's complement, and the next one is the diminished radix complement, which we call the R minus 1 complement. For the binary number system, the two complements will be the 2's complement and the 1 complements, where 2's represent the radix complement and 1 represents the diminished radix complement. For the decimal number system, we will be having 10's complement and the 9's complement, where 10 is representing the radix complement and 9 is representing the diminished radix complement or r minus 1 complement. Now we will discuss that how we generally calculate this complement term. There is a standard formula for calculating the radix complement and the diminished radix complement. Suppose we have any number which is represented by capital N, and there are n number of small n number of digits are required to represent that number. Then we calculate its radix complement or the r complement using this formula. Simply r is the represent the radix or the base to the power n minus the given number. In this case, n is not equal to 0 because for n is equal to 0 we will get a 0 to 7. So for rn minus n, we will have to just perform this operation. This will give us the complement of that number or the r's complement of that number. If we want to calculate the diminished radix complement, or you can say the r minus 1 radix complement, in this case the formula is slightly different because we only have this rn minus 1 term. So we have a minus 1 extra term here. This n again represents the actual number, while the small n represents the number of digits. So if we want to calculate the radix and the diminished radix complement, we will simply apply these two formulas to calculate these terms. Now we will first be discussing the tens and the nines complement. These two are used for the decimal number systems, because for the decimal number system the r's complement is the tens complement and the r minus 1 or the diminished radix complement is the nines complement. Say we have a decimal number which is represented here as this one. In this case, this number is represented in a form of say 6 digits. So if we just apply the formula which we discussed in the last slide, we simply apply that formula, because r here is equal to 10. So 10 to the power 6 minus this, the number, the 10 to the power minus 6 will result in this, while just subtracting it with this number will result in this thing. So this is basically the complement of this number. The tens complement of 01238 is 987602. So this is its tens complement. We simply just need to apply the formula and calculate these things. There is another shortcut for calculating this tens complement, or in fact we will be discussing all the complements here, and there are a shortcut for almost all of them. So the shortcut for calculating this tens complement, because if you see that for calculating the tens complement you again have to use some multiplication and the subtraction. So what we are doing is our aim is to reduce or simplify our subtraction process. But if you look at this subtraction is still involved in this, and there is an additional process of this thing involved. So we are adding up the complexities. So there is another shortcut by which we can calculate this tens complement. Say we have this number, decimal number here. What we do is first we subtract the least significant number. This one here is the least significant, and this is the most significant number here. So this is the least significant digit, and this is the most significant digit here. So what we do is we subtract the least significant digit with 10 and all the rest of the numbers with 9. So this will result in the complement of this number. So if you look at this, if we have 10 minus 8, this will result in 2. We will get 2 here. Then all other numbers are subtracted by 9. So 9 minus 9 will result in 0. Then 9 minus 3 will result in 6. Then 9 minus 2 will result in 7. Then 9 minus 8 will result in 8. 9 minus 1 will result in 8. And then 9 minus 0 will result in 9. So in this way, you can see this result is same as this. So in this way, you can easily, or you can say quickly, calculate the tens complement for any given number system. You just need to remember this thumb rule. Now, if we want to calculate the nines complement, for the nines complement, what we do is we again have the same number here, and it is represented with the same number of bits, 6. What we do is we have an extra -1 term here. So 10 to the power 6 minus 1, and then we subtract this number from the original number. So if we do the subtraction, we will get this result. Again, there is a thumb rule for easily calculating this ninth complement, which is that if we just subtract all 9 from all these digits, subtracting 9 minus 8 will give us 1, then 9 minus 9 will give us 0, then 9 minus 3 will result in 6. So if we subtract all the separate digits from 9, we will get the nines complement. And if you can see that for the both nines and the tens complement, the only difference is of 1. If we add a 1 in the nines complement, it will become equal to the tens complement. So this is how we calculate the tens and the nines complement. And now we will be discussing the binary number systems complement, which are the twos complement and the ones complement. First, we will be discussing the twos complement. Say we have a binary number which is represented in a form of 7 bits like this. We want to calculate first is twos complement and then is ones complement. We have calculated this twos complement in this way. We just simply apply the formula which we have discussed, r to this power small n minus capital N. So this term will result in this, while we will have to subtract this number from here. So this will result in this. So for this binary number, we have a complement equal to twos complement equal to this number. Now again, there is a shortcut or a simplified method to calculate this twos complement, for which is that what we do is for all the least significant zeros, we remain them unchanged. All the least significant zeros will remain unchanged, while first one will also remain unchanged. So we will get all these terms at same. 1 0 0 0 will remain the same, and after that what we will do is we will just reverse all the remaining bits. Reversing all the bits means that we will be changing 1 with 0 and 0 with 1. So if we combine these two parts, we will get 0 1 0, then 1 0 0 0, which is equivalent to the twos complement of this number. So in this way we can easily calculate the twos complement. And now the ones complement. Say again we have the same number and we apply the formula which we discussed in the last slides. And now we have an extra term here of minus 1 here. So for the 2 power 7 minus 1, we will get this result here. In this case, we will be just subtracting these two numbers. This will result in this. So this is the ones complement for this number. Again, we can calculate it in a very easy way. The easy way is that for any given binary number, if you just reverse all the bits, meaning convert 0 to 1 and 1 to zeros, this will result in the ones complement. So you can easily calculate the ones complement like here. This. And you can see that for this we have a result here, and if you see both of them, they have just a difference of 1. So both of the complements have a difference of plus 1. So we have discussed not only the formulas, but we have also discussed the thumb rules for all the twos complements, ones complement, tens complement, and the nines complement. If you look at the hardware perspective, you can see that if we apply the formula, it involves a lot of computation, because you have to calculate the power of 2 to the something or the power of 10 to the something, and then you also have to provide the subtraction part. So we started with easing or simplifying the process, but we ended up in making the system a whole complex. But if you observe it a little bit more, that the ones complement and the tens or the nines complement, in these cases, this thumb rule or the shorthand is very simplified. How? Because if you just look at the thumb rule for the ones complement, how we can calculate is that we just reverse all the bits. We just change all the bits that are 0 to 1 and all the bits that had a value of 1 to the 0. So by just changing the values of all the bits, we can easily calculate the ones complement. So by using this method instead of applying this formula, it is very easy to calculate the ones complement. And suppose if we are required to calculate, the if we are required to calculate the twos complement, what we do is we first calculate the ones complement, and then just we add a 1 here, which will result in the twos complement. So similarly, for the case of the decimal, you have seen that the nines complement, it is easy to calculate because we have to subtract a 9 from all the digits. Because for the hardware implementation we will be dealing with the binary number systems, so most of our focus will be on this one. Whether we are calculating the twos complement or the ones complement, we will be using this thumb rule quite often, because this is the most easier one. It is very easy to just reverse the value of the bit instead of taking the power of 2 and subtracting with some number. So whenever we are required to take the ones or the twos complement, the best way is first we take the ones complement, which is just the transposing all the bits, reversing all the bits, and then if we want to calculate the twos complement, we will simply add plus 1 to this, well, which will result in the twos complement and the ones complement. In the next lecture, we will be utilizing these complements in the subtraction procedure. We have only discussed what is the complement and how we calculate complement of any given binary number or the decimal number. Kindly do read these pages from the book for the better understanding. Thank you.